So we're going to finish up graphing sine and cosine today by looking at period change. Okay, a period change, it's the last transformation we need to do. Okay, we've done phase shift, which moves it left and right. Vertical shift moves it up and down. We did amplitude change, which was our first stretch, okay, stretching it vertically. A period change is going to stretch it left and right, horizontally. Okay, and it has the form y equals sine or cosine. And it's when you put some number in front of x. Okay, so there's an example, sine 4x. Our book just represents some number as a generic letter, and they decide to use this thing that looks like a W. Yeah, it doesn't matter what letter they use, but that's the Greek letter omega. All right. So they just decided, let omega be the number that's in front of x, and when we do an example, you'll actually have a number, like cosine 2x. Okay? So in this case, omega is 2. In this case, it's 4. In that case, it's a half. All right. So this is like amplitude change because it is multiplication, but you're not multiplying in front. You're multiplying inside the parentheses. Okay, so it makes a big difference whether you multiply inside or outside, and then whether you add or subtract inside or outside. All right. Now, what do you think 4 is going to do? Do you think that's going to stretch it out, or do you think 4 is going to compress it? Compress it? Some people say stretch it. Well, remember I said there's two transformations that do exactly what you'd think. We looked at those yesterday. And then there's two that do the opposite of what you think. A phase shift is one of them. You do the opposite. Let's look at this one. Right. So in blue, I'll graph the original. In red, I'll graph sine 4x. And speed it up a little bit. There's the original. And there's sine 4x. So it did compress it. It does the opposite of what you'd think. Big numbers compress it. Big numbers actually make it smaller. Okay, if I did something like sine 2x, it's still going to compress it, but not as much. Okay, the closer this number gets to 1, the less it'll compress. Okay, so there's the original. And there's the new one. Still compressed, not as much. Okay, what if I do 0.5x? Yeah, that's going to stretch it out. Okay, so now we're going to take the original one, and we're going to make it longer. Okay, and we heard what that sounds like. As you stretch a sound wave out, what happens to the pitch of it? As you stretch it out, yeah? Yeah. Yeah, it gets lower. Okay, so the more stretched out we make this wave, the lower pitched it gets. Okay, what happens as we compress it? Yeah, we get not louder, but higher pitch. Sometimes certain pitches are easier or harder for us to hear, so it might sound louder, but I'm not really changing the volume. Okay, leaving the volume the same. Right, so that'd be a higher pitch kind of sound. Sometimes if you have like an older TV, anyone ever have that feeling like you can tell a TV's on? Because you hear like, you almost hear something maybe like this. Yeah. You hear like that sound. And, some chargers do that too. You plug them in, cell phone chargers. Yeah, you can kind of hear that noise. Okay, so it's a frequency. It's a high-pitched frequency. All right, so just as a reminder, okay, what period changes you're going to do? It's going to stretch or compress the graph on the x-axis. Okay, stretching and compressing on the x-axis. Okay, keep that in mind because that's going to tell us what's going to change, and then what's going to stay the same. Okay, what do you think the key number is in front of x? If it's bigger than this number, it's going to compress. If it's less than this number, it's going to stretch. 1. Okay, 1 is the point at which it changes from stretching to compressing. So if the number in front of x, which again we just use the Greek letter omega, that's fine. If that is bigger than 1, it's going to cause the graph to compress. If it's between 0 and 1, okay, like a fraction, 1/2, 0.25, anything like that, the graph is going to stretch. For this lesson, omega won't be negative. Okay, we're never going to look at something like this. We could, we're just not. Right? So you won't have to worry about negatives in front of x. It's either going to be bigger than 1 or between 0 and 1, like that. Okay, so any questions on just kind of in general what a phase shift sounds like, what it actually does to the picture, or when it's compressed or when it's stretched? All right. So next thing we have to figure out is where do the five original points go? Okay, so to figure that out, we're going to use a formula to help us. This formula will help us out. Okay, when we're stretching and compressing it, we're changing the period. Okay, here's kind of a basic sine graph. How many degrees do we have to go through before we go all the way back to the beginning? 360. Yeah, normally it's 360 or 2 pi. But if you compress it, you're changing that. Okay? Maybe it's going to be something like this. So now it's going up, it's going down, it's going back up in half the time. So you don't have to go all the way to 2 pi. Now you only have to go halfway before you are going to repeat your cycle. Right? This formula tells you basically where the end point of the period is. It tells you how many degrees you have to go through, or radians, before it's going to start over. It's 2 pi divided by the number in front of x. So in this case, you do 2 pi. You could divide by 4. It would tell you what the period is. Or in this one, you do 2 pi divided by 2. Or in that one, you could do 2 pi divided by 1/2. Right, so this is what the last 2 multiple choice questions on the test are going to look like. It's going to say, find the period of the following. Okay, you don't need to graph it. All I want to know is the period. Okay, first of all, just by looking at it, we have a 2. Is that going to lengthen the period? Or is that going to shorten the period? It's going to shorten it. Okay, this is the original period. I'm expecting this number to get smaller. It's going to shorten. Okay, so we should get something smaller than 2 pi when we're done. Okay, in my formula, t equals, okay, what always goes in the top? 2 pi. Okay, that never changes. Okay, what goes in the bottom depends on what's in front of x. Okay, so what's in front of x this time? 2. Okay, and if we can simplify that, we will. Okay, what's 2 pi divided by 2? Pi. Yeah, pi. Is that pi a smaller number than 2 pi? Yeah, it makes sense. It's shortened. In fact, this time it's shortened by 1/2. Okay. Any question on that? Find the period. That's all you have to do. All right. How about this one? What would be the period of cosine 5x? And if it doesn't reduce, then don't reduce it. Just leave it. George?
2 pi over 5.
Yeah. 2 pi divided by 5. Okay. And that is shorter. That's even shorter than this one. Okay. Take 2 pi and divide by 5. That's a pretty small number. So we've really shortened the period 5 times as much here. Made it 5 times shorter, 5 times more compressed. Right. And one more. Sine of 1/4 x. Okay, Cooper, what what goes in the top of my fraction? 2 pi. This time I'm just going to write it like this. I'm just going to make it a fraction. 2 pi over 1 because of the number I have in front of x. Okay, Bruce, what's going to go in the bottom this time? 1/4. Okay, so now I've got a fraction divided by a fraction. Trevor, how do I do that? Yep. So take 2 pi, and what did you say? Multiply by? Well, right now it's divided by 0.25. I don't want to divide a fraction by a fraction. But I do like the idea of changing it to multiplication. By what? No. If you divide by 0.25, it's not the same as multiplying by 0.25. Yeah, by 4. What did you do? How did you get 4? Brandon. Yeah, you multiply by the reciprocal. All right? So if you have a fraction over a fraction, take what's in the bottom and flip it. Multiply, and what do we get? 8 pi. Is 8 pi bigger than 2 pi? Yeah. And it should be. Okay, we have a number between 0 and 1. That's going to stretch it out quite a bit. So if you were to graph something like that, might look like that. It's very stretched out. Okay, any questions on finding the period of a function? All right. What if we had something like this? And I asked you, what's the period? So find the period. What would be my fraction I would set up to find the period? Eddie?
It would be 2 pi over 2.
Yes. What about all this other stuff? How come it doesn't matter? We're shifting it left and right. Maybe we're shifting it down. We're stretching it. None of that affects the period. That is the only thing that affects the period. What if I did this? What's the period now?
It's still pi.
Still pi. That shifts it up and down. That doesn't affect the period. What if I said, what's the amplitude?
You'd multiply the y by 3.
Okay, if you were going to graph it, but if I just said, write down the amplitude. What's the amplitude of this? 3. The amplitude is 3. Okay, what's the amplitude now?
3.
Still 3. What's the amplitude now? Still 3. Right? So what I want to do is just write down what each one of those numbers does, so we kind of know. So let's just write it in general. Sine. I don't remember all the letters we used exactly. But I think we used D yesterday. All right, so let's do them in the order we learned them. What's B do? It could be plus or it could be minus. But Emily, do you remember what B does, or what we call it?
Left and right.
Yeah, it's going to move it left and right. And what's the name of that?
Phase shift.
That's a phase shift. Good. Okay, then we've got, I think this is the next one we learned. Okay, putting a number in front. Well, Justin, you remember what that one does? Yep, changes your amplitude. That's your vertical stretch. We can call it an amplitude change. Okay, this is the next one. Okay, adding or could be subtracting a number at the end. Tony, you remember what that one does? Well, it's not the one we're doing today, and it's not either one of these. The vertical shift, yeah, it moves it up and down. Okay, vertical shift. And the last one we're doing today, that's the period change. Right, so in terms of graphing, you would never have a problem that has all of these in it to graph. I could give you one like up above and just say find the period, but I wouldn't have you graph this. It's not hard to graph it, you just have to do it one step at a time. And you have to do it in a certain order. This would be like doing 4 problems on your homework. That would be the amount of work it would be. It's 4 things. Right? But on your test, you're only going to have to graph one thing at a time. Okay. Questions on that? All right. So last thing before we can graph, we just have to find out where those 5 key points go. All right. First thing, let's figure out which column stays the same. Okay. If I take a picture like this, and I stretch and compress it, just take one point and follow it. Yeah, the x's are changing. This point is moving left and right, but it's not moving up and down. So the y's are going to stay the same. So copy those down from the original table. All right. Now to find the new x's. All right. Where do we start? We're talking about sine. What's the first x value for sine? 0. What's the first x value for cosine? Not y.
Oh.
X. 0. Okay, they're both 0. So if you take 0 and you stretch it, okay, multiply it by a number. What happens when you take 0 and multiply it by a number? It stays 0. Okay? Or if you take 0 and compress it, multiplying it by another number, okay, it always stays as 0. So no matter whatever you multiply 0 by, however you stretch or compress 0, it always stays 0. So the first x coordinate is always 0. Okay, that one won't change. Okay, the next coordinate we're going to find is the end point. Okay, so we've got the beginning. Now we need the end. Well, the end is the length of the period. Okay, it's however long the period is. Okay, do we have a formula that can calculate the length of this period? What is that formula?
T equals 2 pi over w per omega.
Yeah, t equals 2 pi over omega. This formula tells you the length of the period, and the length of the period is where it ends. Right? So that gives you the beginning, and it gives you the end. Okay, so I've got the first one, and I've got the fifth one. I need the second, third, and fourth. Okay, the next one I want to find is the third. Okay, I'm going to find this one. What's the location of the third coordinate compared to the first and the fifth? Where is it relative to those two? Right in the middle, exactly in the middle. Right? So let's say you had 2 numbers, like 2 test grades, and you wanted to know the one that was in the middle of the 2. How do you find the middle of 2 numbers? You average it. Okay? So to find the third x coordinate, you're going to take the first one, the fifth one, and you're going to average them. Okay? And we're going to be averaging 2 things. So to average 2 things, you add them up and then take half of it. Some people say add them up and divide by 2. It's the same thing. Okay? Add them up and then take half of it. Okay? That's going to give us the third one. And we're going to use the same kind of logic to get the rest. Okay? Where is the second coordinate relative to the first and the third? It's right in the middle of them. Okay? So once we have the third one, we can take the first one, take the third one, average them, and that'll give me the second. Okay, So the second coordinate is the average of the first and the third. And what do you think about the fourth coordinate? How are we going to get that one? The average of which two? Yeah. Take the third and the fifth and average them. That's the whole point of picking points that are equally spaced. So we could do something like that. Okay, so your fourth x-coordinate is the average of the third and the fifth. Okay, for some numbers, this is pretty easy, especially when you get whole numbers, no decimals. Okay, but when you have fractions, it can be a little bit of work. You've got to find a common denominator and deal with that. Right, so the first one I do, I'll make it one that could be like the worst type of one we could have in terms of the arithmetic. And then after that, I'll do a couple that are super easy arithmetic. Okay, so we'll do about 3 graphs, and if we need any more, we can. If not, we'll do some other stuff. Okay, does everybody have the steps? Let me leave them up. So our first one I want to try to graph is y equals sine 2x. All right, now at this point we know all the transformations. Okay, this is how it'll be written on the test. I am not going to tell you what it is. You have to look at it and decide, is it a phase shift? What is it? Okay. What is this one? Sine 2x. And it's probably what we're learning today.
Period change?
That's a period change, okay? Because we got the number in front of x. All right, so for a period change, stretching left and right, what stays the same? We're going to stretch left and right. Yeah, we're not stretching up and down. We're not changing the heights. All the heights, all the y's stay the same. Hey, Aaron, can you tell me what my y values are for sine? 0, 1, 0, negative 1, 0. I thought it was 1, 0, negative 1, 0, 1. That's for cosine. All right. So just make sure when you do this, you got the right table. Okay. Some people copy the wrong table. You lose 5 points right there. Okay. And if you copy the wrong y values, chances are your graph is going to be wrong too. All right. X's. Okay. What's our first x value for every period change? It's always 0. Okay, that wouldn't be true if I was giving you more complicated problems. Okay, if I was giving you a problem that had a phase shift and a period change at the same time, it wouldn't be this way. Okay, but since I'm never going to give you a period change with anything else, you can use this trick. All right, we got the first. Now I want the fifth. Okay, what's my formula to get the fifth coordinate? Yeah. T equals 2 pi, and in this case, over 2. And what does that reduce to? Yeah. So this one ends at pi. Starts at 0, ends at pi. All right, now we're going to average. Okay, we got the first, we got the fifth. Leah, what's the next one we find?
The third.
Yep, we get the one right in the middle, the third. Okay, so on some scrap paper somewhere, take the first, take the fifth, we add them up, and then take half of it. Okay, that's how you average two things. Add them up, and then take half. Or divide by 2. It's the same thing. 0 plus pi is pi, times a half. So we get pi over 2. Any question on that one? That's the third. Okay, the third one is, well, they're all really important to get right. But if you get the third one wrong, then we're going to mess up the second and the fourth as well, because we're going to use pi over 2. Right, Jacob, how do I get the second?
Just the first and third.
Yeah, we're going to average the first and the third. Okay, so take the first, take the third, add them up, then take half of it. Okay, when I add this up, I'm going to get pi over 2. 0 plus pi over 2 is pi over 2. And what's half of pi over 2?
It should just be half of pi. Wouldn't it be 1/2 pi over 2 or something like that?
So to do this, you just want to multiply straight across.
Oh, okay.
Yeah.
It would just be pi over 2. Over 4, sorry.
Pi over 4. All right, so that's our second one. Okay, and now we got to do the fourth one. Okay, Sarah, how do I do the fourth one?
You take the middle of all three and the left.
Yep, we're going to average which two?
The third one.
Yeah, we're going to take the third one and the fifth one. Okay, this is the trickiest one to do arithmetic-wise. All right, so take pi over 2. That's the third one. Okay, pi is the fifth one. Add them up and take half of it. All right, what do I have to do to add these together?
Get a common denominator.
Yep, I need a common denominator. Okay, what's my common denominator between 1 and 2?
2.
2. So I'm going to multiply the bottom by 2 and the top by 2. So I got pi over 2 plus 2 pi over 2. And then take half of it. Hey, Rachel, what's pi over 2 plus 2 pi over 2?
3 pi over 2.
Yep, 3 pi over 2. Take half of it. That's 3 pi over 4. Okay, and that's the worst type of problem you can have arithmetic-wise. Okay, any questions on the table? Okay, our last step is just to graph it. Always label your axes using the values for x. Since we're going to use 0, we're not skipping it. You don't have to worry about skipping anything. The only time you skip lines is if you don't use 0. That's when you got to be careful. So we got pi over 4, pi over 2, 3 pi over 4, and pi. Okay. Sometimes people look at that and they're like, that's not equally spaced. These don't look like they're the same distance apart at all. They are. Okay. If you changed them all to degrees, they're all 45 apart. The first one is 45, 90, 135, 180. So they are equally spaced. The highest is 1, lowest is -1. 0, 0, 1, 0, -1, back to 0. Okay, and there's our sketch. Any questions on the sketch? All right, so the last two we're going to do, the arithmetic is a lot easier. Okay, much, much easier. All right, cosine of 1/4 x. Let's set up our table. Okay, this time, Justin, what stays the same? Y's. Okay, we're going to stretch it left and right. Make sure you copy these down from the cosine table. Okay, different y values than last time. Okay, Kobe, for a period change, we always start at what? For x, we always start at 0. Now, look at the number in front of x. Okay, 1/4. Okay, so to find our new period, it's 2 pi divided by 1/4. Did we already do that? Yeah. That's a problem I already did with you guys. Right here. This was sine 1/4. We're doing cosine 1/4. It's the same period though, just different y values. So 2 pi divided by 1/4 is 8 pi. Okay, we already went through that. All right, so we're going to end at 8 pi. Okay, now we're going to average them, but we're going to get very nice numbers. Okay, to find the third, take 0, add 8 pi, and take half of it. Okay, Brandon, what does that come out to?
4 pi.
4 pi. Okay, the next one, let's see if we can just do in our head. Okay, 0 plus 4 pi is 4 pi. And what's half of that? 2 pi. Last one. What's 4 pi plus 8 pi? 12 pi. And what's half of it? 6 pi. Done. Okay, a lot easier that time. Any questions on that one? Yeah, I think that's also much easier to see. They're all equally spaced. They're all 360 degrees apart if you did it in degrees. All right, let's take our graph. Go from 1 to -1. Okay, every problem today is 1 to -1. We got 2 pi, 4 pi, 6 pi, 8 pi. I labeled it that way because I just didn't have enough space. 0, 1, then we're at 0, -1, 0, back to 1. Okay, any questions on that one? Yeah,
Or you did the 1/2.
that 1/2.
Yeah, when you do the problem.
Oh, when I'm averaging?
Yeah.
Oh, some people just say divide by 2. So like if you want to average two things, you add them up and divide by 2, or add them up and take half. Just, it's the same thing. Yeah. The only reason I'm not saying to divide by 2 is because if you add up and divide by 2, like look at this one. You'd have pi over 2 plus pi over 1. I think that looks more confusing than writing it this way. Because now you've got fractions over fractions and stuff. That's why I don't write it this way. Okay, any other questions on this? All right, last one. Let's try this one. Okay, Leah, what's my first step?
Do I have 2 over 5, 2?
Okay, what are you finding?
Your fifth.
Fifth. Okay, I like the idea of how you found the fifth. But anything you want to do, a few things before that? I do agree, we're going to have to find the fifth one eventually. But I would do a couple things first.
Make the table, plug in the y.
Yeah, make the table, fill in all the y's. Okay, you don't have to, but that's the easy part. I would do that first. George, what are my y's?
For sine, it's going to be 0, 1, 0, -1, 0.
Good. Okay, and one more thing I would do before we find the fifth x-coordinate. Yeah, let's do the first x-coordinate, which is always what? 0. Every sign problem for a period change is always going to start just like that. Now I would do what Leah just said. Do 2 pi, which I would make it a fraction, and then divide by pi over 2. Okay, Amanda, how do I take a fraction and divide by another fraction?
Reciprocal.
Yep.
The denominator.
Reciprocal of the denominator. So I'm going to take 2 over pi, and what do I do with that?
Make it 2 pi. I mean, 2 over pi.
All right. So that's the reciprocal, but do I do anything with it, or is 2 over pi my answer?
You multiply it at the top.
There we go. So we're going to take the top, we're going to multiply, and now we're going to flip the bottom. Okay, so what's going to happen there? Oh, Bria? Yeah? Go ahead.
4 pi over pi.
Okay, so you get 4 pi over pi. And Brianna, anything I can do with that?
Reduce it.
Yeah, what does it reduce to? You got this. Got the same thing in the top and the bottom. So what happens when you got pi in the top and pi in the bottom?
They cancel out.
They cancel out, so what are you left with?
4.
Yeah, you just left with 4. All right, so if you had the same thing, you could have canceled it out right here too. All right, so all we get is 4. So now our arithmetic's going to be super easy. We don't have any pi at all to deal with. What's the average of 0 and 4? 2. The average of 0 and 2? And 2 and 4? Done. Okay. So this is a problem where technically I wouldn't take off any points if you didn't label these. Because I said if you're not going to go by ones, you need to label it. Well, I am going to go by ones, but I'll still label it. But if you didn't, you wouldn't lose points on this particular problem. Okay. Everything goes by ones. Okay. And graph your points. 0, 0, 1, 1, 2, 0, 3, negative 1, 4, 0. Okay, any questions on that one? All right, so that's a period change. Okay, that's the last transformation we need to know. All right, so now I think with the time we have left, we'll look at a couple special things. Okay, kind of how with sound frequencies. Homework will be a worksheet, okay, which I'll give out in a little bit. Okay. First thing I want to take a look at is what's called an LRAD. Okay. Anybody ever heard of that before? It's called a long-range acoustic device. Okay. Basically what it is, it's like a laser for sound. Okay. If you had like a laser and you pointed at someone, which you shouldn't do, but if you did, that laser would only be pointed at that one person. Somebody standing off to the side or behind the laser, they wouldn't see it. That's kind of what this is. It's a speaker. And if you aim it at somebody, they hear the sound. But if I'm holding the speaker, I wouldn't hear it that well. In a room I would, because it would echo. But if we were outside and I pointed the speaker at you, you would hear it. Other people on the sides and behind me wouldn't. So it's like a spotlight for sound. It's very, very directional. All right, so I'm going to show you a couple uses, and there's a little video about how they use this on like some different cruise ships and police departments and kind of what you can do with it. All right, so let me just bring that up.
In response to the terrorist attack on the USS Cole in October of 2000, American Technology Corporation created a device like no other. LRAD, the long-range acoustic device.
A wave of the future.
A high-tech tool developed by the military.
A high-tech sonic weapon.
Long-range acoustic device, or an LRAD.
The long-range acoustic device, or LRAD, is like an audio spotlight. When you're standing alongside of it or behind it, you can carry on a normal conversation, but get directly in its beam, and the sound becomes almost painful.
Because of its weight and size, the LRAD is easy to transport, easy to set up, and mounts almost anywhere.
Cruise passengers now barely escaping that pirate attack.
We're learning more about that stunning pirate attack.
This magnificent cruise ship attacked off the coast of Africa by 21st century pirates.
The LRAD's usefulness was most recently demonstrated in November 2005 when pirates attempted to attack a cruise ship off the coast of Somalia.
It has 26 languages and about 100 different remarks like put your hands on your head, or lie flat on the ground, or turn around and do such and such.
The system clearly enables us to enforce the Naval Vessel Protection Zone at all times.
The fact that an individual was informed of the reasonable consequences of his actions and continued to defy legitimate authority, they are personally responsible for whatever happens next.
Whether initiating communication or warding off unknown adversaries, the LRAD has proven effective more than 80% of the time and has saved countless lives in the process. From American Technology Corporation, LRAD, the long-range acoustic device.
All right, so you could see some different uses for it. Some had it mounted on like a police vehicle, and it's a kind of sound that if you were at like an event and they wanted to disperse a crowd, you probably wouldn't want to stand around and keep hearing it. So it's an idea, basically it's a weapon, but it's supposed to be less violent than using like tear gas or something like that. It can still cause damage, definitely cause deafness. Okay, if you hear it for a long period of time. Did everybody hear that what the LRAD sounded like? It's kind of like that siren kind of sound, but they can also use it as a microphone. So like if they wanted to communicate instructions to someone, like they said, it's got different languages, or they can just talk on it, and people down, very, very far away, even farther than like the trees, would very clearly hear the person, because it's a very, very directional sound. So a couple different uses for that. All right, let's see. Another thing we can look at, DTMF. Has anyone ever heard that abbreviation before? DTMF. It stands for dual tone multi-frequency signaling. Okay, and that's basically how phones work. Okay, regular phones, cell phones, okay, any type of phone. All the buttons that you press on your phone, they're all frequencies. In fact, it's exactly 2 frequencies played at the same time. Right? So we didn't really get into sketching things like this. Okay, that's a graph of 2 frequencies at the same time. Okay, it's got a pattern to it, kind of like a sine wave, but a little more complex. All right? And there's a chart right here that shows you every button you can press on your phone and what the frequencies are when you press it. Okay, so let me show you, like for a 1. Okay, if you play 1209, okay, what I'll do is I'll just play that one to start. And turn down a little bit. Okay, that's a 1209. Doesn't really sound like you're pressing anything on the phone. Let me play 697. Again, doesn't really sound like anything, but put the 2 together and it's going to sound just like you're pressing a button on the phone. I need to separate them. Okay, that's what it would sound like when you press a 1. Now, if you change that frequency a little bit, okay, say instead of 697, you did 687. Okay, it's going to sound off enough that it's going to sound funny. Okay, listen to it. Okay, and the further off we get, okay, it starts sounding kind of weirder and weirder. All right, so what you can do is, if you're in any kind of like menu system where it's asking you to press a button, okay, I can go into my voicemail. Okay, I'll go into my personal options, and it'll say like press 4 to do this, or press 1 to change your greeting. Well, instead of pressing the buttons, I'll generate the frequencies, and my phone will think I pressed the buttons. All right, so I'm not going to touch the phone, but it's going to think I'm pressing buttons. All right, so as I do it, it has to be kind of quiet so it can, because I'm far away from the speaker. But I think the first thing I need to press is a 4. So let me get that ready. It's 1209 and 770. Right, and I got to turn it up a little bit. All right, so let's call my voicemail and see if this works. Hopefully I have service. All right, I think I can go underwater with it though. I really can.
Main menu. To listen to your messages, press 1. To send a message, press 2. To check receipt of a message, press 3. To change your personal options, press 4. To disconnect, press star. To establish or change outcall notification schedules, press 1. To exit, press star.
I'm not ready.
Are you still there? To establish or change outcall notification schedules, press 1. To exit, press star. notification on or off, press 1 to change administrative options. Press 2 for greetings or recorded name. Press 3 to change notification options. Press 4 to exit. Press star. Goodbye.
Right, so just by the phone hearing the frequencies, it's thinking I'm pressing the buttons. I could do the same thing with this kind of phone. Okay, it's got a dial tone. The dial tone is 2 frequencies at the same time. And if you could generate the frequencies fast enough, you could make a call without pressing the buttons. And then when the call rings, you know how you hear it ringing? Well, this is the frequency for the ring. It's 440 and 480 played at the same time.
Did you figure this out?
I looked this up. I did all this, like, this is what I'm doing right now, I figured out, but all the frequencies, I looked them up.
Like, did you know that it went off, like, I always thought when you hit 4, it was like the button, not the noise.
Yeah, I mean, yeah, it's that frequency, that's
What
how.
about smartphones?
Yep, smartphones, work the same way. Yep,
It's not, it's just going off the sound.
it just hears the sound. And even if you have it on silent, it can still work, it still works the same.
What about
Yeah.
texting?
Texting? Texting, I don't think uses frequencies. That's more of a,
It's the actual button that
that's characters, yeah. That's a little different. Okay, but all telephones that you make a call on, like voice calls, it uses frequencies. All right, so let's see. Last thing, take a quick look at, okay, is how we can connect it to music. All right, so music is, basically it's playing multiple sounds at the same time, and we call it chords. All right, so with a phone, we play 2 frequencies at the same time. With music, you might play 2, 3, 4 frequencies at the same time. Right? And basically, there's only so many frequencies our ear can hear. Right? We can hear from a high end to a low end, and then even in between, like if I play this frequency, 440, or I play 441. Most people probably can't hear the difference between 440 and 441. Okay, they're too close. So the point is, there's only so many frequencies we can hear, only so many things we can tell the difference between. Will there ever be a point where we've taken every frequency we can hear, arranged it, all the different ways we can arrange them, and there'll never be any more new music? Okay, could that happen? Okay, so this guy takes a look at that, and then we'll finish up with one other video about music.
Did the phones pick up, like, if it was just 1 hertz off, would the phone be able to pick that up? Or?
I think 1 hertz might be okay, but I think if you were up to 10 or 15 hertz off, I don't think it would work. No, but 1 hertz would probably still work. Yeah. All right, let's take a look at this.
The iTunes Store contains 28 million different songs. Last.fm carries 45 million songs. And the Grace Note database of artists, titles, and labels contains 130 million different songs. That's a lot. If you were to listen to all of the songs in the Grace Note database, one after the other, in a giant playlist, it would take you more than 1,200 years to complete. But since there are a finite number of tones our ears can distinguish, and because it only takes a few notes in common for 2 musical ideas to sound similar, will we ever run out of new music? Will there ever be a day where every possible brief little melody has been written and recorded and we are left with nothing new to make? A good rule of thumb might be to say that if modern recording technology can't distinguish the difference between 2 songs, well, neither could we. So let's begin there, with digital downloads, MP3s, CDs, and a calculation made by covered in Bs. Digital music is made out of bits. Lots and lots of bits. But each individual bit exists in one of 2 states, a 0 or a 1. Now what this means is that for any given, say, 5-minute-long audio file, the number of possibilities, mathematically speaking, is enormous, but mind-blowingly finite. A compact disc, which samples music at 44.1 kilohertz, is going to need about 211 million bits to store one 5-minute song. And because a bit can exist in two states, either a 0 or a 1, the number of possible different ways to arrange those 211 million bits is 2 to the 211 million power. That value represents every single possible different 5-minute long audio file. But how big is that number? Well, let's put this in perspective. A single drop of water contains 6 sextillion atoms. 6 sextillion is 22 digits long. It's a long number, but the total number of atoms that make up the entire Earth is a number that is about 50 digits long. And estimations of the total number of hydrogen atoms in our universe is a number that is 80 digits long. But 2 to the 211 millionth power, the number of possible different 5-minute audio files, is a number that is 63 million digits long. It is a number larger than we can even pretend to understand. It contains every possible CD quality 5-minute audio file. Inside that amount is everything from Beethoven's Fifth to Beck's Loser. It even contains a 5-minute conversation you had with your parents when you were 3 years old. In fact, every one of them. It even contains every possible conversation you didn't have with your parents when you were 3 years old. But it is finite, not infinite. It's cool to think about, but it doesn't come very close to answering the question of this video, which is how many possible different songs can we create and hear the difference between. So for that, we're going to need to narrow down our hunt. On Everything 2, Ferris Lepidoptera made a calculation that involved some assumptions that I think helped narrow the field down in a really nice way. She took a look at the total number of possible different melodies you could create within one octave, containing any or all of the intervals we divide octaves into. Of course, sound frequencies can be divided much more granularly than that, but giving ourselves more notes might mean we could make more technically different melodies, but they wouldn't necessarily sound any different to our ears. Now, given a single measure containing any combination of whole, half, quarter, eighth, 16th, or 32nd notes, she calculated that there would be this many possible unique measures, which is a smaller number than we had before, but to put it in perspective, this is how many seconds old the universe is. Uric DE's calculation is even more specific. He stayed within one octave, but instead of looking at a complete measure, he only considered the number of unique combinations of 8 notes. He also assumed that typical melodies as we know them today only contain about 3 different types of note length. For instance, quarter, eighth, and 16th, or whole, half, and quarter. To be sure, that will most likely not always be true. Musical tastes hundreds, thousands of years from now will most assuredly be different. But given melodies as we know them today, across 8 notes over 12 intervals, there are about 79 billion possible combinations. We're getting relatively small here. I mean, under this definition of melody, 100 songwriters creating a brand new 8-note melody every second would exhaust every possible melody within only 248 years. But it's still a huge number, way bigger than the total number of songs that have been written that we know about. So you can quite safely say that, no, we will never run out of new music. But here's the rub. If that's the case, why are there so many commonalities between songs, even across hundreds of years? How come so many songs kind of sound the same? I mean, if we have more possibilities than we could ever exhaust, why is Twinkle Twinkle Little Star, the Alphabet Song, and Baa Baa Black Sheep all the same melody? My Country 'Tis of Thee and God Save the Queen, interestingly enough, are the same song. Love Me Tender is exactly the same as the old American Civil War song, Aura Lee.
Sunshine came along with me, and I always will.
And a seemingly uncountable number of songs merely sound like other songs. The SpongeBob SquarePants theme has a very similar cadence to Blow the Man Down. SoundsJustLike.com is a great resource for exploring this further. It'll show you two songs and how they sort of sound alike. And when it comes to musical chords, it's almost as if there's no variety at all, as was famously shown by the Axis of Awesome's 4 chords. I've linked.
Right, so with the time we have left, yeah, we're going to take a look at that video. We'll probably end up finishing it tomorrow. Okay, while we're watching that video, I will pass out the homework for tonight, and then we'll have our test tomorrow.